Section 20, Dark Ages, First Stars, and Reionization. This section was updated February 2025. The Dark Ages start sometime after 370,000 years after the Big Bang, Z equal 1090, end of recombination, and last scattering. In this image, time flows left to right on a logarithmic scale. The image shows us what was happening in the universe at different times. We just covered recombination, and we will now move forward in time to the Dark Ages. After recombination and CMB last scattering, the scale factor continued to increase and density and radiation temperature continued to decrease. Matter was no longer in thermal equilibrium with radiation. There were no stars yet, no starlight. After last scattering, the temperature of what we now see as the cosmic microwave background was 3000 Kelvin. Very intense, visible range orange light throughout the universe. As the universe expanded, the CMB background light did not abruptly become dark invisible light. First, the light would have gotten deep orange and less intense, and then red and less intense. Then dark invisible light, but still glowing intensely in infrared light. Around 1 million years after the Big Bang, CMB temperature was 1630 Kelvin, a deep orange color, and the average ordinary matter density of the universe fell below the matter density of the best vacuum created on Earth. Hydrogen and helium were neutral atoms, but lithium was still ionized. Around 4 million years after the Big Bang, the CMB temperature was 700 Kelvin, no longer visible to our eyes. This is equivalent to being inside an 800-degree Fahrenheit oven. We will take this as the start of the Dark Ages. This use of the word dark by cosmologists means no starlight yet, so cosmologists may give its beginning as the time of recombination or last scattering. Around 10 million years after the Big Bang, the total matter density of the universe fell below the present matter density of the Milky Way galaxy. There had been slight overdensities and underdensities of dark matter on all scales since the first decades after the Big Bang. At CMB last scattering, with baryon acoustic oscillations, some baryon ordinary matter overdensities coincided with the small-sized dark matter overdensity regions that would later become the first galaxies or galaxy clusters. These regions continued to contract relative to the universe's expansion, though they were not yet gravitationally bound. The dark matter could not collapse toward the center of the gravitational well because it could not shed energy. It remained what astronomers call a galaxy's dark matter halo. The ordinary matter contracted toward the center of the dark matter halo, eventually shedding half of its kinetic energy in a messy process called Reionization. It is not that the particles all moved straight toward the center and collapsed into a single huge black hole. The ordinary matter was a gas whose temperature increased as it collapsed. Infrared light radiated by the gas escaped to travel the universe, but the total intensity was less than the CMB, and we do not detect it. The messy process produced smaller-sized local overdensities of ordinary matter that would gravitationally collapse to produce the first protostars and then stars. The first stars in the first galaxies inside the smallest size dark matter halos, which had been contracting since the first decades after the Big Bang. The average radiation temperature of the universe fell below 140 Kelvin, slightly less than half of room temperature, before the first stars would form. Colder than Antarctica, but warmer than liquid oxygen. But temperature was hotter within the galaxies. The first stars shine at 50 to 100 million years after the Big Bang. Z equal 48 to, say, 29. This is the beginning of the end of the Dark Ages and the start of reionization. Books written before the James Webb Space Telescope began operation in 2022 say that the first stars started to condense, begin fusion, and shine sometime between 50 and 400 million years after the Big Bang, ending the Dark Ages. The redshift for that time is between 48 and 11. So we would see their starlight redshifted into the infrared. The Hubble Space Telescope cannot see these first stars, but the James Webb Space Telescope can see early galaxies with the first stars to shine and early quasars. The James Webb should provide better understanding and confidence about the first stars and first galaxies to shine, but I have not kept up. The current range for the first stars to shine seems to be 50 to 100 million years, so redshift of 48 to 29. The first stars to shine were believed to be more massive, hotter, and more luminous than the Sun, like O-type stars today, more than 5 times hotter and more than 10,000 times more luminous than the Sun. They emitted a lot of ultraviolet light. This ultraviolet light reionized nearby hydrogen gas that had been neutral since recombination and throughout the Dark Ages. There would be a large bubble of ionized hydrogen plasma around each such star. As more large hot stars formed and shone, and also to a lesser extent quasars at the cores of galaxies, more of the hydrogen reionized, and there would be an ionized bubble around each galaxy. This bubble is meant to show, say, the first galaxy that reionized the bubble around it. Then the reionization extended between galaxies until all the gas between galaxies throughout the entire universe became reionized and has remained ionized ever since. This includes all cosmic voids. So here we're showing the bubbles getting larger and sometimes touching, and then more and more of them are touching or overlapping, and then eventually there's no more bubbles because the entire universe is reionized. Cosmologists believe that all the hydrogen and intergalactic gas and cosmic voids throughout our visible universe, and therefore presumably our entire universe, became fully ionized by 650 to 1200 million years after the Big Bang. so redshift of 8 to 5. So the period 50 to 1200 million years, or maybe it's 100 to 650 million years, is called the Reionization epoch. We cannot see the emitted ultraviolet from those early stars that was absorbed reionizing the hydrogen. When reionization finished, the intergalactic medium stopped absorbing the ultraviolet light, which then traveled the universe. So we can see the original ultraviolet from Z=5 quasars, now redshifted to infrared, but not always from more distant ones. Lithium would also have become ionized. I don't know if helium became singly ionized or doubly ionized. Cosmologists have this short, funny history of our universe in 15 seconds. First, there was nothing. Then there was something. Then there was hydrogen. Then there was dirty hydrogen. First, the dirty hydrogen was ionized. Then it was neutral. Then it was ionized again. The dirty hydrogen is hydrogen with helium and lithium. We will see later how that comes about. We've already seen how the dirty hydrogen was ionized before recombination, and then it became neutral at recombination, decoupling, and last scattering, and started the Dark Ages. And now we have seen how it became ionized again in the reionization epoch. So intergalactic hydrogen was once again a plasma, as it was before recombination. However, the universe had expanded, and the density of hydrogen ions, electrons, and photons was more than 1 million times lower than before recombination. Photons could scatter off this plasma, but the scattering rate was much lower than before recombination. The scattering rate of photons off electrons was now lower than the Hubble parameter expansion rate of the universe. Also, the mean free path for scattering was larger than the Hubble distance. This plasma is not opaque, but not fully transparent either. It is optically thin. Cosmologists believe that about 1 out of 16 CMB photons have scattered off the reionized hydrogen, so there is some irreducible fuzziness to the CMB imaging. Astronomers and cosmologists want the James Webb Space Telescope to identify the times when the first stars, galaxies, and quasars started to shine. Astronomers and cosmologists also want to know how early galaxies, stars, and eventually Type 1a supernovae were different from today. Data from Webb seems to show mature galaxies much earlier than expected for the standard model of galaxy formation and evolution. This may result in model changes which may obsolete chapters of earlier books. Sometimes you will see an exaggerated clickbait title for an article saying that everything previously known about the universe is wrong. These typically refer to the need for a better model of galaxy formation and evolution, not that all of standard cosmological model is wrong.